Guy here. It's Tuesday the 10th of November 2020. Time for your weekly update on the 10-4 Eleanor. Eleanor is coming along great. We are actually at the 99.5% wired state. Power has been applied. Some of the bits have been programmed into the state machine. In fact, you can hear and see the oscilloscope running in the background. Not a lot to show you. I will show you the pulse in a moment that says that she's alive. Then we will go through a series of short clip videos which show you how we got to this point. We are now at the boundary of transitioning from hardware construction to software construction. We'll go into that in those clips. This will be about a half an hour plus a few minutes of the evolution of the construction of the board, and you'll see that in relatively short order. What else can I add? Here's a bit of good news. If you recall those close-up focus issues I've been having in the last several videos, I believe I've found a solution. I obtained a wide-angle adapter for my Canon camera that will allow this camera to focus much closer and to give us a better picture. So, you're welcome. Let's get on with our program, shall we? Let's take a look at the scope waveforms as they exist at this moment, and then get into our videos. Here's three of the waveforms coming out of the state machine at this moment. One of them is going in. The upper trace is our master clock running at 4.096 megahertz. To the left on the second trace is the state machine reset pulse. It is 1 clock cycle wide. We'll look at that in a moment. Below that is frame reset. Now, just for fun, I've made it 48 clock cycles wide, just to make it ambitiously large so that we have no doubt that it will be resetting the video address counters for the picture memories. So even though it looks kind of wide on the screen there, it is very narrow compared to the 151 clocks that make up a single pixel time of the image data being pumped out of the memory chips. So let's expand on the traces right now and look at our reset pulse. Too much? Okay. I don't like that, but give me a moment and we will fix that. There we go. Now we can expand it. Alright, what we're looking at now is the reset pulse on the second trace relative to our 4.096 megahertz clock on the upper trace. So you can see that our reset pulse is 1 clock cycle wide, and then on the bottom trace, not the very bottom, the yellow trace, you can see the start of the frame reset pulse, and between the rising edge of the state machine reset and the falling edge of the frame reset, this is address 0 of the memory chip, and this would be address 1, and this pulse is programmed to fall in address 0. Why is it 1 clock late? That's because of the output data latch on the memory chip. So I will have to compensate for that in the timing calculations for that pulse memory. So that's just to show you some of the simple issues we will run into. I will elaborate more in the video clips to follow. So let's shorten the time here so that you can see the pulse trains and have an idea of when you look at an oscilloscope, sometimes you see the clock in the upper trace looking like a solid band. Why is that? Well, that's because of the amount of time that we're looking at on the screen. This is 10 microseconds now, 1 microsecond per division. Now it's 2.5 microseconds across, 25 microseconds wide, and you can just see the end of our reset pulse, our frame counter reset pulse. So there we are looking at a 50 microsecond window from here to here, and our pulse within it. The actual cycle time of the frame of video is immensely long compared to this. This is a very tiny slice of time. The frame is 80 milliseconds, which is an immensely huge amount of time compared to this. So now let's go back in time a bit and look at the construction of the boards and their progress. Alright, we're going to install the first run of the master clock line, M clock, and it's going to go from the clock oscillator to the 3 state machine counters and to the state machine output latch. State machine clock wire is in. One of my viewers commented that he didn't believe that I was using PLCC packaged flash memory chips. Why didn't I use DIPs? Well, 32-pin DIPs are huge, enormous. They would not have fit on this board, not in a layout this nice. And he was under the impression that wiring these is kind of a problem. Well, as you can see the socket outlines, they are 2 squares of pins, and the pin numbering can be quite goofy on these until one gets used to it. And when I'm wiring, I made myself a key right here that I use to make sure that I wire the pins correctly. And once you have this diagram, it's not so bad. To answer that question, so the next round of wires that I'm going to do will probably be the counter outputs address bus to the memory chip, and that entails 19 wires that have to be cut, run from the counter chips here and wired to this PLCC here. So the next time you see this, those wires should be in place. The first 8 address lines are connected to the state machine flash prom. Okay, the address bus from the 3 counters to the memory part is wired. Let's see if we can zoom you in without going too much out of focus. That is a lot of wiring. Not really. It did take me several hours, but I did take several breaks and cooked lunch and a whole bunch of other things. Went to the store, so I don't know how many minutes I spent actually working on it. Alright, the next phase is to wire the data bus over to the latch from the memory chip. So, stand by. For you, it'll be instantaneous. The state machine outputs are wired to the latch. The last thing to go in now will be state machine reset, which goes back to the counter clear pins on the 3 counter chips. And that will close the loop. And in theory, the state machine would operate right now and put out pulses, assuming I had a memory chip programmed with some pulses. So, we're at that point. The entire state machine is now wired. Now I'm going to have to program a flash prom to generate pulses, but I don't think I'm going to stop wiring. I'm going to keep going. Well, the state machine is completely wired. Sorry for the low light, but that's so that you can see the LEDs. We got plus 12, minus 12, and plus 5. That's so that lab guy knows there's juice on the board and doesn't solder away on the chips while they're powered up. He's been known to do that. Using our infrared camera, the back of our fingers, we'll check for hot spots. If you're working on a board and you're wondering if there's a hot spot, use the back of your hand. Just put it like this, run it around. If there's a hot spot, listen for these telltale signs. Blood-curdling screams, the smell of burning flesh, and sizzling meat stuck to something that has too much current flowing in it. That's some lab guy advice to you folks. Okay, this is the evening of November 6th. It's about 10:30, 10:45 or so p.m. and we have wired up the state machine, and I've looked at it with the scope. The state machine chip, which is labeled state machine, is not programmed correctly. That is the program for the Philocam that's in there. I just wanted to see it making pulses, and indeed it is outputting pulses on the scope. So I'm not going to show you the scope because there's no point. There's nothing right about it. So there you go. The first power to the 10-4 Eleanor. At this point, it's Saturday night. I think it's the 6th or the 7th, the 6th. I don't know. 6 p.m. The state machine is wired down here, and it's operating. I programmed the reset bit in the memory chip, and it works. And the wiring of the video memory address bus has begun. It's being driven from the low order video counter. The next video counter only has 3 bits involved, and it'll be done very quickly. And then the frame output port over here, driven by the computer, will be wired in 8 more wires running over and down like that. It's a lot of work. And I'm in danger of actually running out of yellow wire before the weekend is over. And I can't buy any more before Monday. So, anyways, let's look at the other side of the board. I put the chips in and labeled the memory parts so that we'd know which memory was which. State machine, red EEPROM, green EEPROM, a blue EEPROM. So progress continues, as you can see. All the address lines to the video memories are now connected, both from the video address counters, the ones that churn out 2 kilobytes at a time in a loop, and the 8-bit latch, which selects one of 256 images to display. So the latch is here, the two counters are here, and the memories run this way, and you can see the parallel lines running down. There's 19 address lines on this. It's 1/2 megabyte of memory, 1/2 mega word, 3 bytes, red, green, and blue, and 500,000 of each. So quite a few, 524,288, I think. I think that's the correct number. So the address bus is connected. The data buses next will come off of each memory chip. There's a memory here, here, and here, and they will jump over to the latches. They'll go this way and this way to the latch and D to A converter, latch, D to A converter, latch, D to A converter. So those wires go in next. But I'm running out of yellow wire. I'm almost out. I'll probably run out tomorrow. It's I don't know. It's 8:15 p.m. right now, and tomorrow's Sunday, and the store where I get this is closed. So at any rate, that's where we are at with this board. See if I can line that up so you can see it. That's our board right there. Coming along. She's almost wired. Almost. What would you call that? Halfway. Maybe just a little more than halfway. So we're getting there. It's not pretty now. It was pretty before. But it is organized. You can see some form in the chaos. It only looks chaotic. I leave the wires kind of loose like this in loops. That's so that they can be moved aside when you need to get down to a pin that's been covered up down here. You can pull them aside and get in there to work. So you have to leave a little bit of slack in these wires. I don't know what else to tell you about it, other than it is coming along. We're almost there. Soon, this project will change from hardware soldering and wiring to programming of memory chips. So, stay tuned for that as well. Carrying on. Good morning. It's Sunday, November 7th, 2020, and we are resuming work on the 10-4 Eleanor. Today, this morning, I'm going to wire the data buses from the memory chips to the latch chips. One thing I have not mentioned up to this point, don't know if you'll be able to see them, but if you look in front of, these are not the latches. If you look in front of the latch chips there's a skinny black component between the memory and the latch. That's an RPAC. It's 8 parallel resistors that are tied common on one end. That end, the common end, is grounded. That is so that when the chip enable, or more precisely the output enable of the memory chip is disabled, the resistors will pull the inputs of the latch low automatically. This is how I insert video blanking. During blanking, I disable the output of the memory. The RPAC pulls the inputs of the data latch low, and the data latch will now output zeros on each clock pulse. And it will continue to do so until I enable the memory bus output again. And so that's the blanking mechanism that I've designed into this. It's very elegant and very simple. the output of the 8 D-type flip-flops is coupled through tri-state buffers, which I've permanently enabled. They're not connected to a bus. Each latch is connected directly to its own digital to analog converter, so that 8 data bits are converted from a count of 0 to 255 to an analog voltage of 0 to 1 volt. And that's how the digital data is converted back to analog video. Each D to A chip is buffered by an op amp. There are 4 op amps in each of these 2 chips, and 2 op amps are devoted to each D to A. The output of the D to A goes to an op amp buffer, and the reference input of each D to A chip, the top of the R2R ladder, is fed by a voltage that will be provided by a buffer op amp in these chips, so that there's a nice, clean, steady, low impedance sourced reference 1 or 2 volts. I don't remember the exact voltage, but it's one of those two, which the chip uses to generate its analog output. This leaves me 2 op amps, which will be used for the process of summation of sync to the monochrome output of the board, the Y in RGBY. The RGB is apparent. It's the red, green, and blue outputs for color televisors. But you also need sync, and the Y output contains both monochrome video and sync. The sync comes from the state machine and is summed in to the analog monochrome video, which is produced by taking the red, green, and blue through a resistor matrix, which I will cover in some detail later, and converting it to the Y signal. In color television, Y is your monochrome component. It refers to the black and white, and it's synthesized from 30% red, 59% green, and 11% of blue. And this will give you the equivalent of the output of a black and white source. To that video, I add the sync pulses, and it goes out as the Y signal. That'll go to the cathode ray televisor, and if we were running the color big televisor, all 4 signals will go to that. And that is how these outputs will work. We are getting very close to that point. And that is that the output of the memory chips now will go to the data latches, the reclocking chips. This removes glitches produced by memories when you hold their enable on and grind a counter through the address locations. During the time that the address bits are changing, the output data on the memory chip can be glitching. There can be random addresses formed by very minute timing differences in the address bits. So we send the data to the D latches and clock them on the next clock pulse, so that the output of the D latch, all 8 bits change together, and in fact all 24 bits will be changing synchronously on the output. That's the deglitching mechanism. So that's the essential operation of the memory data bus coming out. So I'm going to get on with wiring that up, and you'll see that next. Alrighty. I don't know if you can tell, if you can see them. The data buses on the memory chips go around the bottom in a little U shape like that and come over to the 3 latch parts, and they come over the top of the vertical runners, kind of tying them down a little. The next stage will be to run the outputs of the D latches over to the D to A converters. Alright, that phase is done. You can see the wiring of the DACs over here. We've got the 8 data lines coming from the data latches over to the D to A converters. All of the ground lines of the D to A converters were wired up. They're 10-bit D to A converters, and I'm running them as 8-bit, so the 2 LSBs are tied to ground so that we're using the 8 MSBs, most significant bits. And yeah, that gives us a resolution of 1 part in 256 instead of 1 part in 1024. So the data bus to the D to A converters is wired up. Wow, I haven't run out of wire yet, and it looks like we're going to make it. So the next stage will be to put in the analog circuitry, and then some connectors. I'll have to write some software for the Arduino. I'll have to load some pictures into into the 3 picture ROMs, and then debugging will begin, and that's probably a day's worth of work. Maybe not. So there could be software errors. There's most certainly there's wiring errors. I keep finding them. Those power lines. It's just like, let's solder these to random pins. I hopefully have now sorted out all of the miswired power pins and taken care of that. So, at any rate, we're moving right along. Okay. I've wired up the op amps. Most of them, the DAC op amps. I have to install the potentiometers now and construct the luminance sync circuit. So there's going to be a total of about 6 potentiometers that I have to install and get connected up. But the D to A converter circuits are now completed, and we're ready to move on to that final phase, and then we go into chip programming mode and then bounce back and forth between software, hardware, software, hardware, software, hardware until the thing works. So not bad progress for about 3, maybe 4 days of a couple of hours a day working on it. This is the point we're at right now at 12:30 on Sunday the 7th of November 2020. I've begun initial placement of the potentiometers. This will be red level, green level, blue level, red to luminance level, blue to luminance level, and sync level in the luminance signal, in the, call it the composite video output, the monochrome output. And that constitutes the locations of the potentiometers. An 8-pin header strip will go on this edge over here. There will be a header strip on this side over here next to this chip to receive the I2C bus from the Arduino. And these are 2 LED strips that I've put in. Each one has 4 LEDs within. They will reflect the frame number that is selected in binary. This is to confirm that the I2C is communicating. This thing will be like a Christmas tree when we get done. It'll have lights on it. So that's where it's at the moment. I have to solder all these things in now and proceed. There's still quite a bit of work ahead. There's the software. a little bit more wiring, and then it boils down to software. Lots and lots of software. So the board is almost ready. The back is wired pretty much 99%, 98%, so we're good to go. Here's an update for you. All 7 pots are installed, not 6. So we have red DAC level, green DAC level, blue DAC level, luminance level, RY level, BY level, and sync level. That's a good Lord, that's a lot of adjustments. That's a lot of adjustments. Holy moly. And the Rain Man in me is screaming bloody murder because I had all gray pots for most of the values except this one. I have a blue one. I will probably be changing that. It is just grinding my gears. It shouldn't matter, but it does. After everything else that I managed to keep beautiful on here, I had to have one cockeyed blue pot. And no, I have a red pot for the red gain, for the RY gain. I didn't have a blue one for the BY gain, so maybe I'll change that one as well. I'll change both of these to red and blue later, but probably not, because the red ones are not of the same style. And this is crazy. The little screw head is slightly smaller than on these, and that also would grind my gears. You know, it's just a matter of making it look good. You know, aim for your best work if possible. If possible. It's pretty busy on the back. Pretty busy on the back. As you can see, when we transition from the digital zone to the analog zone, it thins out pretty quickly. The last of the digital is these little wires here in 3 places. And then out here in the op amps, it settles down. There will be wires running to the pots in the op amps. Not much more, not much more, a few resistors. All of the passive components on here are surface mount. You can probably barely see them. And that's good. That's good because this keeps the top of the board just literally all chips for the most part. No fields of passive components. So that's the aesthetic considerations. All right, moving on. Well, it's, I don't know. It's nearly 8 p.m. Sunday night, the 7th of November, 2020. And I'm still tinkering away. When I get a spare moment, I add a few more wires. I fix the mistakes I find, and they are legion. But she is almost done, and then we run into software. I've even completed the red, green, and output wires are now connected to the output connector. So yeah, we have an output connector on this side with the power connector up here. And inevitably we're going to have a computer interface connector over here. This white strip is new. It's 8 LEDs in a bar that will display the frame number as you select frames, or they'll flicker like mad if it's playing a motion sequence. So it's coming along. It's almost done. I'm going to go tomorrow and buy more wire. I need more yellow wire. I did not run out. I did not run out, but it's inevitable at the rate I'm going. I can see the inside of the spool now. So we're nearing the end of that. But there is the Eleanor Sunday night. There's the rat's nest. We had a bit of a wiring error over here. I caught it. It fixed up okay on the board, but the schematic now looks stupid because I had to actually flip the chip upside down. And no big deal. It's no big deal. That was to make the 8 data lines connect between the I2C receiver and the frame synchronizing latch, and make those come out right on the schematic. So now the power pin for the I2C chip is on the bottom and the ground is on the top. My Rain Man is, well, normally he'd be losing it, but he looked at it and he goes, that's adequate. So that's where we're at this point. Sorry for these short updates, but that's the way it's going to be. It beats watching me solder for 12 straight hours, putting it on, taking it off, putting it on, taking it off. So I'm getting excited with anticipation. Soon this thing will be outputting a signal. The last bit of circuitry, as far as I know, that I need to wire at this point, these 3 pots down here, which are the composite video output, the black and white NBTV signal output adjustments. These 2 upper pots mixed down red and blue, mixed with the green, which is on a fixed resistor, and produces a luminance video, and the bottom pot is the amplitude of the added in synchronizing signal. So between these 3 we synthesize our output black and white signal, or servo sync for a mechanical TV that's color, and so on. And then we also will have the red, green, and blue. So it will output simultaneously red, green, and blue video and composite black and white video, all synchronous, of course, and able to run black and white and color televisors of the NBTV standard. It's Monday the 9th of November 2020, and I believe I've just soldered in the last wire on this board. Yay! Okay, so at this point I now have to create the bit patterns for the state machine ROM and program all of them into the chip. Currently only the state machine reset signal is programmed, so I'll be spending some time this morning doing that, but I have to run out to the parts store and get parts, buy some wire, and so at any rate, Monday the 9th November 2020, this board, the 104 Eleanor, is first order complete. It is ready for testing. I also will have to write software for the Arduino because the stupid I2C port comes up in input mode, making the frame latch up a 255. So I have to remember to put a test pattern at location 255 in the video ROMs so that this thing will generate an image immediately. I'll probably put some color bars there. So I'll have to create that file as well. So at any rate, that's where we're at. Work continues. This is the updated drawing of everything. I am in the process of debugging the state machine at this point. and trying to figure out some anomalies that I'm getting. It's, of course, doing what you expect new hardware to do. That is, doing exactly not what you expect it to do. So I'm looking into it. Also, after consideration of looking at my state machine and everything, I realized that the original timing ideas I had were too simplistic, and I'm working on making it better. And this, of course, results in a much more complex basic program for creating the binary drive files that go into the state machine ROM. And currently I need to sort out the fact that the counters that drive the address bus have their own output latches. Now they should only be delayed by the 244 nanoseconds of the master 4.096 megahertz clock. So they should be almost instantaneous. The 4 megahertz clock gives us, in our 80 millisecond frame time of 12.5 hertz video, it just gives us an immensely fine granularity in terms of time slices where we can cut and place our edges. We can trim those suckers to within 244 nanoseconds of perfection. So we have overkill in that respect. But what was going to happen was that the blanking signal, the way it was originally envisioned, was going to eliminate one column on the side of the picture and one row, if you will, across. One row across at the edge and one row down, and it's arbitrary which edge because I get to pick that. And I got to looking into it in greater detail, and I've come up with a system that allows me to have blanking, line blanking period, that is before and after, very, very minute amount of time before and after the sync pulse, and still get all 32 lines and all 64 rows of pixels out of the memory and up to the televisors. So you won't lose a column in a row. When you only have 32 pixels, 64 pixels in a line and 32 lines, you can't afford to give one of those away. You can't. You want as much on the screen as you can get. So at this time, that is the state of the state, and I've been working on it off and on throughout the day, but I had chores to run, I had to buy groceries and so on. I did buy a new roll of yellow wire, so we're good there, and so on. And anyways, took care of the things I had to take care of. Did manage to put in an hour, hour and a half, maybe 2 hours working on timing diagrams, which are bloody nightmares. Those will be covered in a deep dive when they are finally sorted out. I'm not going to hammer you folks with my description of what I'm expecting to achieve before I get there. You'll see it when it's working, when I sort out all the issues with it and kill all of the incorrect presumptions on my end of it here. So at the moment, what we've got is, you see, 2 scope probes, and I've got these nifty little header pin things that plug onto my 9 test points that I built in right along the output of the state machine chip, so I can look at all 8 outputs of the state machine and our master clock signal. I want to work out, as I started to say, what the clock delay is from the time of the reset of the address counters to the data actually appearing on the output of the data latch, so that I can correct for that with programming offset in the memory, so that the pulses will come out truly on the clock cycles where I want them. So there will be a slight 2, maybe 3 clock cycle bias involved on that, and so on. So details, details, details. When you start getting into these kinds of things, it's the details that will eat you alive. But the key is to know that there are details. Once you know there are details involved, you can address the details. Now that is all for now, and I'll be right back. So that was the look at the construction phase of the physical board, and how we've arrived at this point. This has been your weekly update, because I know you like when I put out videos. I didn't beat you to death with the construction, the real-time construction, simply highlights. And we will continue from there. So until next time, this is Lab Guy, out.